Everyone. It's a great pleasure to present to this conference. I wished I would be in Beijing. I miss my time in Beijing, and I hope very soon I'll be able to join again. Wiji, thank you for the introduction. As the title of my presentation shows, we have been working on helical piles for many years now, and it's increasingly used in applications that involve dynamic loading, and it's also used in projects located in seismically active regions. And actually, observations during recent earthquakes demonstrated superior performance of helical piles compared to other types of piles, as well as compared to shallow foundations. In today's presentation, I'll talk about some of the work that we've done recently related to the performance of helical piles under seismic loading. And that will include 2 experimental programs and 2 finite element modeling exercises for these programs, which will help us to understand some important characteristics of the performance of helical piles. So let me first introduce what helical pile mean, because I'm not sure everyone knows or have used these foundation elements in practice. A helical pile, as shown in this picture, is a steel shaft that is fitted with 1 or more helical plates, and these helical plates help install the pile in the ground by applying a torque to the pile head through a torque machine like shown here. So the helical plates help install the helical pile into the ground like we do a screw in the wall. But then when they are located in position, they also serve as a load-bearing element. And that actually provide 2 very significant advantages. One, because we apply this mechanical torque to place the pile into the ground, we have lots of correlations between the required torque for installation and the ultimate capacity of the pile. So that allows us to immediately know the capacity of the pile. The second feature of this pile, because a lot of the load bearing is taken through these helical plates, we can actually position the helical plates in competent soil layers to provide the required capacity, but also in the case of liquefiable soil, you place the helical plates in non-liquefiable soil, hence you can ensure continued capacity of the foundation element and minimize the settlement, as we will see from the observations of the experimental work and numerical models exercises. And now, more recently, helical piles of large diameters have been used in increasing practice. I've used some of these helical piles with a diameter up to 40 inches, 1 meter in diameter, and the helices themselves as large as 2 or 2.5 meters in diameter. So they provide very large load carrying capacity. They provide significant lateral resistance, and definitely they can be used for major infrastructure projects. They can be installed very quickly and reduce the cost of the foundation system. Today, I will talk about certain features of helical piles that apply to the situation of liquefying grounds. I show here in the picture the work by Kibunevsky, which demonstrated the differential settlement that occurred to a building and during the Christchurch earthquake in New Zealand. And as you see here, the settlement varied between 29 centimeters on one side to 4 centimeters on the other side of the building, which can introduce significant bending stresses in the supporting frames and cracks and significant damage to building, and sometimes total collapse. On the right-hand side, a similar situation for a building in Alaska that experienced also a significant settlement due to liquefaction of underlying liquefiable soil layers. And if we place these structures on helical piles, we can actually change the situation dramatically. So here's 2 examples of that. You see here on the left, a house supported on helical piles in Big Lake in Alaska for the same earthquake that we've seen the previous one that was not supported in helical piles. You see this house is intact, no differential sediment, in a beautiful situation. Similarly, the house on the right-hand side, a two-story house that actually survived 2 earthquakes in Anchorage and Alaska. And again, it's intact, no signs of distress, no sediment or differential sediment. So the research motivation for this and the crust of this presentation, that helical pile performance under axial loading is very well understood. We've done a lot of research in that. We understand how to characterize the capacity and use it in design. We found that the axial capacity of helical piles is actually greater, in many cases, much greater than an equivalent driven pile. So it provides that efficiency in terms of utilization of material. A single helical pile performs under lateral static cyclic loading, same as or better than driven pile, custom-based pile. And it has been now the focus of research for applications in wind turbines and offshore structures, where the piles will be subjected to dynamic loads and in some cases, seismic loading as well. And all previous dynamic testing single helical piles included loads applied at the pile heads. I myself have done a lot of that, but we haven't really done real seismic loading on helical piles, neither single piles or helical pile groups. So we started to look at that. So the first experimental program that I will share with you today, the work that we have done using the large high performance outdoor shake table test in testing facility in University of California, San Diego, which we use to conduct full-scale shaking tests of helical piles, single piles, and pile groups. And as you see in the images on the right here, we installed several helical piles and we loaded them with concrete masses to present the mass of the support structure. And in the bottom image, we have the situation where we connected 4 piles in a group and we used the skid to simulate the way of the support structure. And then, of course, for single piles and pile groups, we applied shakings that represented real earthquakes to varying levels of peak ground acceleration to see how the piles perform under the different levels of risk elevation. We installed the piles in well-graded sand. The height of the sand bed was almost 4.5 meters. It was compacted to about 90% relative density. And then we installed the piles using the method of installation that we use in practice. So the same mechanical torque, using the same equipment and measuring the torque as we install the piles. It's exactly the same way. So it's full-scale piles installed exactly the same way as field work. We instrumented the soil bed with accelerometers. We instrumented the piles themselves. We instrumented the skids that were placed on top of the piles. And we also had string potentiometers to measure the movement of the shear box that contained the sand. As part of this testing program, we conducted 5 different testing programs. In day 1, we tested the sand only without piles. In day 2, we had single piles with no pile head masses to look at the kinematic interaction of the piles. And as you see here, we installed 10 different piles with different characteristics to see the effect of the configuration of the pile on sand performance. In day 3, we tested single piles with head masses that represents the case of a single pile carrying a certain load. Perhaps you can think of it as piles supporting pipe racks or pipe bridges in LNG projects and things like that, where the piles behave as single piles, and we use helical piles for that purpose a lot. And then in day 4, we tested groups of piles where we fixed the pile head into the skid using that we hoped that we are fixing it fully using 2 bolts. And then in day 5, we removed one of the bolts to allow the piles connection to the skid to mimic the pin connection. The piles properties are shown here from 1 to 10. So the piles are either single helix or double helix. And we had one pile for comparison as a driven pile. The piles were carrying different masses, as you see here. So there was some variability in the mass carried by the different piles. And then, as I said, in days 4 and 5 of the testing program, we connected 4 piles together to form the pile group number 1, and the other 4 piles together to form the pile group number 2. We varied the extent of the pile above the ground to look at the effect of that sticking part, because in many applications of piles, you would have a portion of the pile sticking above the ground, and that could have very significant effect on its lateral stiffness and natural period of the system, and hence its response to seismic loading. So as I mentioned before, we installed the piles using the mechanical torque exactly the same way as we do in practice. And here is the measured torque as we install the piles in the ground. And you see that all piles have very much the same torque profile, which indicates 2 things, that the uniformity of the soil bed, but also the performance of the piles is very consistent for the piles that have 88 millimeter diameter and the piles that have 140 millimeter diameter. We instrumented all piles with strain gauges at different elevations, and as I mentioned before, the piles were sticking above the ground different values. We considered that in the interpretation of the results, and later in the finite element modeling exercise, we instrumented the steel skids with accelerometers so we can actually monitor the behavior of the model structure and use that in the processing of the data. The input motions used in this, we have different motions. We used pulse waves with very low peak ground acceleration, so 0.06 G. And we did that to determine the shear wave velocity profile, the damping ratio, the natural frequency, and effect of successive shakings on the soil bed. We also used white noise signals, and these were random signals with constant RMS values, amplitudes, and bandwidth varying between 0 and 40 hertz, and that was done to determine the natural frequency of the system, either soil bed or the piles, single piles or pile group. And then we applied earthquake records, and we used 2 of them because they have different characteristics, because we wanted to evaluate the effect of the earthquake characteristics on the pile's behavior. One was the North Ridge earthquake in California, the other one was the Kobe Takatori earthquake in Japan. Here is this works fine. So this is the shaking test for the single piles, and you see here how the piles performed. And let me say that the concrete masses supported in this are actually representative of true pile load. So as you see here, the piles survive the shaking, no problem. Did extremely well and supported the loads with the high level of shaking. This is the Great Hanshin earthquake, Takatori earthquake, and the performance of the piles was excellent. This is the pile group experiment, and again, it's subjected to the Takatori earthquake. And you see here the movement of the shaking, significant movement. The pile group sustained the loads, no problem. But one observation, I want you to look here at the gapping that opened between the pile and the surrounding soil, because that is a very important parameter that will affect the performance, and we have to account for it when we analyze the results or when we do finite element modeling or analytical modeling for the performance of these types of piles. So now we'll start to look at the experimental results, and we'll focus on the seismic responses as well as dynamic properties of piles. So we looked at, let's say, the natural frequency for the different piles. As I mentioned before, the piles had different diameter, had different masses supported on their heads, and some of them had different stick-up ratios. And as you see here, we found that there are some variability in the natural frequency because of the change in the mass for the piles that have the same diameter. But what most important was the sticking or the free length, as that caused significant variation in the natural frequency. So this is a very important aspect that we have to pay attention to, because this free length part could be done intentionally in many of the applications. When you support equipment, let's say equipment come on steel skids, you weld them to the top of the pile head, but to do that, the pile head has to be sticking above the ground. And in practice, we typically allow 3 to 4 feet stick up above the ground, and that would have very significant effect on the natural frequency of the system. But sometimes this will happen unintentionally when we observe during the shaking of this skid, a gap was opened, gap was created between the pile and the surrounding soil, and that gap represented basically a free length portion of the pile. And that will have a significant effect on the natural frequency of the system and hence its response to the dynamic as well as seismic loading. So this must be taken into consideration when we analyze such piles. That applies to helical piles and driven piles alike. So we have to consider the gap that forms between the pile and the surrounding soil, which will have a significant impact on the response. We also looked at the effect of successive loading, and as I mentioned before, if gaps opens, then the natural frequency will change, and you see here a trend of reduction in natural frequency as the testing progressed from day to day. We also attempted to analyze this. We used the program Dyna6, developed by myself and my colleagues at the University of Western Ontario. It's very widely used in industry for the purpose of dynamic analysis of piles. And as you see, the analysis using the analytical models developed by the Dyna6 actually kind of bounds the observed behavior. So the analytical model, considering the gap formations you see here, if we have no gaps, you overestimate the natural frequency. If you consider very large gap, you underestimate the frequency. But considering the proper gap, we can actually bound the observed behavior. So we're able to replicate the dynamic properties of the soil, and we were also able to look at the seismic behavior as we'll show later. The pile gap was the pile cap axiometer was used to determine the behavior of the pile cap, and as you see here, how the accelerometers from the pile caps were compared with the measurements from the top strain gauges of the piles, and the readings were very consistent. So we started to use the strain gauges for further analysis afterwards. Again, we looked at the different characteristics of the pile group to look at the impact of that on the stiffness and damping of the pile group. And again, one very important aspect, because in practice, we tend to make an assumption either the pile group is fixed into the heads or pinned into the heads. And as I mentioned before, we attempted to fix the heads using 2 bolts to connect each of the piles to the pile cap. And in the case of pinned head, we removed one of the bolts, trying to mimic a hinge connection. And unfortunately, we found that even one hinge, one bolt does not make the connection truly pinned. So this is one aspect that should be considered in the analysis. So the stiffness would be somewhere between fixed and hinged, not truly hinged. Again, we also found that the stick-up part will have a significant impact on the natural frequency of the group, as you see here. So again, this is a very important consideration that we have to take into our analysis. Similarly, the program Dyna6 was used to analyze the group behavior. And again, as you see, the program was able to bound the observed behavior. So we are able to reproduce the observed behavior of the pile group using the program Dyna6. And also we use the program Dyna6 to analyze the response of the pile group to the shaking events that we used, the Northridge earthquake, 100% of that. And we found that to get this perfect match that we see here from the program Dyna6, we had to use a gap of 75 centimeters. So the gap was quite deep, but the shaking was also very strong. Similarly, for the pile group number 2, we found that the gap actually extended to 90 centimeters again to get perfect match like this. So again, the observation we make here, that this gap is a very important consideration that should be accounted for in our seismic design. I will get back you to this figure that shows the effect of the stick-up part. Now we have a stick-up part. When you have a gap, the pile will behave like it has a stick-up part, and that shows how much variation in the natural frequency of the system could happen due to that. Now, these are the seismic responses we measured. I just give a very quick summary of that here. As I mentioned before, we subjected the piles to a number of shaking events, including in the comparison that I'm showing here, the North Ridge earthquake, 100% of the peak ground acceleration, while the Tekatori, we use only 75% here to make sure that the peak ground acceleration value is the same for the two events. And now we will see the effect of the frequency content on the observed behavior. So you see here, the solid lines are for the North Ridge earthquake, the blue line, sorry, the black lines, North Ridge, the blue lines are for the Tekatori. And because of the resonance condition with the predominant frequency of the earthquake, we see that the response to the Tekatori earthquake in this case, for this pile group 2, is, for single pile 2, the response is higher for the Tekatori earthquake, while for the pile group 1, the other way around. The response corresponding to the North Ridge earthquake is higher because now there's a match with the peak, the predominant frequency of the earthquake. So this is an observation that confirms our understanding of the importance of considering the dynamic characteristics of our foundation system when we evaluate the response to earthquake loading. And we also looked at how the system behaves linear and nonlinear as we increase the intensity of the earthquake. So we actually have done the same shaking, so the same Tekatori, the same North Ridge, but we increased it from 50% to 70% to 100% to see how the pile responds. And as you see here, this is the perfect line. If we have perfect linear behavior, we see all points should fall on this line, but as you see, it's not falling on this line. So the behavior is not linear, so there is significant nonlinearity. One main reason for that is the gap that develops, but also some nonlinearity that develops in the sandbed itself. The other thing that I would like to point out that the response of the group, which is much smaller than the response of the pile normalized, and I will come to this point later in the comparison of the results. Also, we looked at the bending moment that develops in the piles. So for single piles, the bending moment increased almost linearly with the earthquake intensity, unlike the deformations. So the bending moment increased as the peak ground acceleration increased. But again, for the group, bending moment is much lower than the bending moment observed for the case of single piles. So the effect of the earthquake intensity showed that the maximum normal force acting on the pile, and this is a very important consideration that I will focus on going forward, the normal force increases as the peak ground acceleration increases. Because for helical piles, one of the main mechanisms for supporting the load is actually the rocking behavior, where the helices provide significant axial resistance, and that helps improve the performance under seismic loading. So the responses of the piles connected together as a group were much better than the responses of single piles because of that rocking mechanism that develops. The pile groups exhibited very close behavior for both connections. Like I mentioned before, we were hoping to have fixed versus bend, but they ended up, as you see here, very similar. And we had just a slightly larger rotations and deflections of the pile head for the pin pile, but it's not really pin. Responses of piles within a group were significantly lower than single piles. So here's the normalized responses. This is the response of the piles within the group carrying the same load under the same excitation, and that is the response of a single pile. The reason for that, as I mentioned before, that the piles in the group behave in the rocking vibration mode, and that transfers instead of flexural behavior, it becomes rocking behavior, and then we engage the axial resistance of the helical piles, and that provides an added advantage for helical piles. Now we do finite element modeling. We've done 3D finite element model where we modeled everything in the system. We considered the nonlinearity, the gap opening, and everything else. And here's a validation for the finite element model, and you see good agreement. And again, we use the same gap values that we established from Dyna in our finite element model, and you see the agreement between the two sets of results. And again, the structural responses for the piles are matching. And then we started to look at the effect of the configuration of the helical piles response. We considered a single helix pile. We considered double helix pile, triple helix pile to see if that makes any difference. We found that the number of helices will increase the axial force carried by the pile, and that will enhance the rocking behavior, will enhance the seismic response in that sense. However, if the helices are embedded too deep, then they are not going to contribute to the flexural resistance in any way. They will only help the axial resistance, and the axial resistance will help the rocking behavior. The second aspect that was extremely important, when you have more helices, the settlement of the pile is much less. So when you have one helix, this is this black line, two helices, the blue line, three helices, the red line, and if there are no helices, this is the case of a driven pile, much higher settlement. So this is one great advantage for helical piles, as we see here, compared to a driven pile with the same diameter. The settlement is much lower for a helical pile compared to a driven pile. Similarly here, there are a comparison in this case showing for a different diameter pile, very significant difference due to the addition of a second helix. So we can use the helical plates to control the response. Now, a second set of experiments that we induced liquefaction in the soil, and we looked at the behavior of the helical piles. In that case, this work was done in my collaboration with Beijing University of Technology in Beijing. We've used the shaking table there, where we tested piles in both liquefiable and non-liquefiable grounds. Here's the test setup. And we again heavily instrumented the soil bed and the piles and the structure supported on the piles. So we're able to we instrumented the piles and we measured the responses for the soil bed and for the piles. And we used the measured responses to validate a numerical model. In that experimental setup, again, we used pulses, we used white noise, and we used the earthquake signal of Wenchun earthquake, which had a peak ground acceleration of 0.3 G. And here's the findings from the test. We had two experiments, parallel experiments, comparative experiments. One was saturated sand and the other one was dry sand. And here are the general observations. You see there are sand boils. This sand has liquefied during the experiment. And in the dry sand, we've seen some fissures, cracks on the surface, but there is no liquefaction when it's dry. We also instrumented the structure, so we were able to get the behavior of the structure and overall behavior to see how it works. We looked at the acceleration within the soil bed, as we looked at the amplification of motion for small amplitude, 0.05 G, and high amplitude, the Wenchun earthquake was 0.3 G. And this one observation is very important in understanding the performance afterwards. For the small peak ground acceleration, significant amplification. For the case of the Wenchun earthquake with 0.3 G, very minimal amplification, actually in some cases de-amplification within the soil profile. Here is the observed behavior for the pile group supporting the structure in the liquefied soil behavior. It was total rocking, and this is very important observation. Please keep this in mind, because remember how helical piles perform better because of the rocking mechanism that it offers. So the experimental results showed the system rotated through a rocking behavior in the liquefied soil, while for the dry soil, there was significant deflection in the piles. Again, for helical piles, they provide fixity in the dense sand layer that exists below the loose sand, and that fixity helped to reduce the lateral response, as well as it reduced the vertical response as well. That is the behavior of the structure. We found tilting at the end of the earthquake. Helical piles will reduce that tilting, as we will discuss later. So here is the numerical modeling exercise. We used the elements that represent liquefiable soil. We used fiber models to represent the pile behavior. So we looked at the nonlinearity of the soil development and dissipation, excess water pressure, and we analyzed the same behavior of the experiment, validated the numerical model by comparing the observations of the experimental results with the calculations of the numerical model. Now we'll start to look at the responses of the piles. So what we see here, single helical pile is this one, double helical pile is this one. So the circular symbols are single helical pile, so one helix, and the squares are double helical piles. And this is the driven piles, reinforced concrete pile. And you look at the difference in the lateral displacement for the helical pile had a maximum displacement that was 1/3 of that of a driven pipe. The reason for this, as I said, the helices provide a fixation mechanism that helps reduce the rotation of the piles, and that translates into reduction of the response of the supported structure itself. For the dry sand, same thing. No liquefaction here, but again, the displacement of the structure supported on helical piles is about 4 millimeters, while the one on the driven piles is greater than 9 millimeters. So as you see, very significant reduction in the lateral displacement. Similarly, if you look at the vertical response of the piles, so the double helix pile here, the red ones, you see the settlement is 1 millimeter here, while the case for the reinforced concrete pile is about 5.5 millimeters. Significant reduction in the settlement due to the helical plates that provided better performance. And now looking at how this happens, we look at the distribution of axial forces. So the blue line here represents the axial force under static loading. So the way that the structure supported in the piles is the share of one pile. But now during the shaking, you see the leading and trailing piles carrying much higher axial loads. And this, again, the point that I mentioned before, that helical piles, when they support a structure like that, will utilize the advantage of the helical plates to provide significant axial resistance, because we place these helical plates in non-liquefiable soils, so we retain the capacity of the piles, but also these helical plates can provide increased bearing resistance as liquefaction happens along the shaft. The load transfers from the shaft to the helices, and the helices mobilize larger bearing resistance, which provides this additional capacity, as you see at the base here. Significant increase in the capacity of the two compared to this part of the capacity under static loading only. So that explains the performance of the helical piles during earthquakes. Similarly, here in the dry sand, again under axial static loading, this is the load per pile. But now, considering the shaking, you'll see a variation of the applied loads. Again, the helical piles here are able to provide rocking resistance through the advantage of the bearing resistance of the helical plates. We also looked at the kinematic response of the helical piles, and that's a very important consideration. Now we are doing actually additional research to see the response of the pile lateral spreading ground. I'm finishing, don't worry.
Good.
So the kinematic response should actually advantage for the helical piles as well. And this is there, and that takes me, sorry. The responses of the helical piles are improved. Again, due to the presence of the helical plates, stabilize the piles, reduces the response. So in conclusion, the helical piles lateral displacements are lower than that for driven piles. The vertical settlement is much lower than helical piles. So than driven piles, sorry. So helical piles provide clear advantage under seismic loading for both dry sites and liquefiable sites. Thank you so much. Sorry for taking a bit long. I'm open for questions.
Thank you, Hesham, for that informative lecture on helical pile applications. We are actually out of time, so I don't know whether we will have time for any questions unless somebody has.
Sorry about running a bit longer.
Okay, so thanks again, Hesham. Really appreciate this. And we are now reaching the end of the morning session. On behalf of the organizing committee, please join me in thanking all our keynote speakers for their highly valuable presentations. Thanks again, and obviously you'll be joining, I guess, after lunch in Beijing time. I think there are some housekeeping messages from Dr. Lanmin Wang.
Okay, thank you, Professor Tama. Ladies and gentlemen, all the activities this morning has finished. In the morning, there were 230 computers was online, and above nearly 500 participants attended the conference. So we have very good beginnings. In the afternoon, all follow-up lectures and parallel sessions will move on online. All participants will attend the conference virtually. So please follow your program book, in which Zoom ID has been printed. You can find the ID and the Zoom system to continue attend the conference. We have 1 hour, 1.5 hours for lunch. In the afternoon, the parallel sessions will start at 1:30. So please keep the time and attend the parallel session at 1:30 Beijing time. See you afternoon. Thank you.